Даниела, здравей! Жени, яла да гледаш камерата. Тошко, здравей! Чакай, аз камерата ще изключа. Моите и това.
Еко, здравейте!
Здравейте!
Ти в момента нямаш нужда от
тебя. Жени, аз пуснах моя екран, обаче не го виждам. Не.
Като сложиш, като отидеш с...
Не,
Аз ви чувам, бе.
Да. Окей.
Само за да видите, че съм с вратовръзка.
Аз ви чувам много добре от Флорида.
Чудесно, Даниел.
Здравейте всички!
Здравей.
Здравей!
Какво ще правим, ако дойдат повече от 100 души? Александра, Сашки, здравей.
Здравейте.
Здравейте от Тексас.
Райчо, здравей.
Да не мислим, че нямаме проблеми. С Зума е за 500 човека.
Добре. Най-после ще съберем целия институт заедно.
Ще направите запис, нали?
И не само института, надявам се. Здравейте и от мен, колеги. Мисля, че и от университета току-що напомних на целия факултет, така че очаквайте голямо присъствие от много места.
Надяваме се. Дано да издържи интернет.
Да, дано да издържи Зума само.
Ами трябва и камерите да ги спираме, вероятно.
Да, звук, камера, само...
Камера, за да нямаме...
Само говорителя. Само говорителя.
И нали ще направите запис?
Да. Ще има запис и после на страницата на центъра, обаче виж към ти.
Да, сега ще махна.
Да. Жени, трябва да си махне микрофоните, защото става... Готово ли е? Сега няма, да. Добре. Ние на центъра винаги има и всичките могат да влизате на страницата на центъра, където има записи на предни лекции и така нататък. Освен това, предполагам, че Тошко ще го качи и в YouTube. Нали, то сега се предава и в YouTube, защото много хора заявиха желание в YouTube да го гледат. И ето, например, Николай Цветков сами се обади преди малко. Нещо има спешна история и не може да следи лекцията. И питаше дали може утре или други ден да я гледа в YouTube и нали, ще направим и това.
Олег, аз имам едно предложение и то не е моя идея. Всеки четвъртък аз хода на една конференция в Италия по Zoom, по теория на групите и винаги преди доклада си правим една снимка. Искате ли да си направим една снимка, както сме се събрали, преди да почне доклада?
Ами може, аз поне не съм правил. Как става това? Или Тошко може да я направи?
Не знам как го правят, обаче преди доклада правят една снимка. Предполагам, че с обикновен телефон може да снимате екрана или нямам представа.
Въпросът е да се наредат всичките хора, които са включили, да се наредат на... Да,
това става с View. Отивате на View и правите Gallery и тогава всички се появяват в Gallery един до друг.
Да. Ами не знам, той Тошко чува ли ни? Тодоре, чуваш ли ни? Това може би нещо... Ами аз не съм правил такава снимка и не знам, те ако са много хора, всичките могат ли да се наредат на един екран?
Не могат, колкото събере екрана.
Ще събере екрана, нали така?
Страница.
Да. Жени, това най-важното е, аз искам да ти благодаря за всичките презентации, нека да се преди да почнем или...
Първо това е общо дело, второ аз съм освен това, че се намали ефект. И аз не платя
Unknown caller.
Олег.
Слушам.
Някой се опитва да драска по екрана с фломастър. Да, това е галерията, това ще се видим, който е тук, ще може да се снимаме, но някой се опитваше да драска с... И това трябва Тодор да види дали може да го оправи, защото върху екрана може да са... сега е изчистено, това е хубаво.
Да му звънна ли или...
Не, сега не се вижда нищо надраскано, не знам кога беше там на някой от...
Аз не знам дали в момента той ни чува. Тошко, чуваш ли ни или... Тошко, ако не ни чуваш, ще ти се обада по телефона.
Това е добро.
Людмила, чуваш ли ме?
Привет. Армен.
Армен, привет.
Привет.
Привет, привет.
Как жизнь молодая?
Привет, Олег.
Привет.
Владо Тончев.
Как си, Владо?
Добре. Аз отначало мислех, че ще е с парола, но хубаво, че е без паролата. Мога да и аз да чуя тази лекция.
Да.
Честита нова година.
Благодаря и на тебе, и на всички.
Честита, Владо, честито и от Петър Кендеров.
И от мен е Даниела. Здравей, Владо. Много се радвам да те видя. Скоро не съм те виждала.
И аз също. Как е? Флорида е топло сигурно, а?
Топло и отворени ресторантите, така че идвай.
Не си за поканата.
Здравей, Владо, и от Райчо от Тексас. И в Тексас е топло, не се оплакваме.
Райчо,
22 града.
добре. Тук студено, ама не ми се пътува в момента.
Да, аз затова не съм се ходила в България, за съжаление, тая година и вече ме е стегнала шапката от всякъде. Обаче си бих ваксината вече, първата доза, опа! И след един месец ще си дойда, като се сложи и втората.
Ние още чакаме на опашката, ама и това ще стане.
Да, те тук отвориха ваксините за 65 години отгоре и guess what, аз съм вече на 65, така че...
Айде, не си признавай.
Людмила, чуваш ли ме?
Да.
Тери, не го виждам да се е включил, при мен е малък екрана.
Като се натисне долу, като се натисне Participants, би трябвало да излезе.
Не, аз тук след малко ще бъда на голем екран, тук съм сега на малък екран и затова няма. А останалите хора? Виждате ли или не?
Тук съм. 138 са.
Не, мисълта ми е Грифиц. Не знам академик Тодоров дали се е включил. И госпожа Ангелиева. И аз, Жени, ако обичаш. Провери, да. Да. Тошко, спря ли презентацията?
Hello.
Добър вечер на всички.
Добър вечер.
Добър вечер.
Добър вечер.
Колеги, здравейте от мен.
Здравейте.
Здравейте. Тери Тао is already here.
Hello.
Hi.
Hi.
Привет, Людмила.
Привет. Армен, тебе понравилась презентация или нет?
Понравилось?
Нравилось.
Да ги видиш.
Danny, is Philip around you or Daniel?
I see him in the Zoom.
Yes.
Okay. Everything's fine. Yeah.
Людмила, движиме се по предварителната програма, нали?
Да.
Окей. След академик Тодоров си ти. Да, окей.
Академик Тодоров е в Зума на линия.
Чудесно.
Але как дела у Йохана? Олег.
Да.
Как дела у Йохана?
Очень хорошо.
Хорошо, отлично.
Да. Йохан, он здесь или нет?
Здравствуй, Армен.
Здравствуй, Йохан.
Okay, I think it's time to start. It's 6:15. So, good evening, good afternoon, and good morning, dear colleagues and friends from all over the world. My name is Oleg Mushkerov, and I'm the director of the International Center for Mathematical Sciences in Sofia, Bulgaria. Today is a very special day for the Bulgarian mathematical community, and at the moment we all feel sad and happy at the same time. Sad because a year and a week ago, academician Blagovest Sendov passed away, and we lost a brilliant mathematician, a dear colleague, teacher, and a friend of ours. At the same time, we are extremely happy because an outstanding mathematician, Professor Terence Tao, is among us to present his breakthrough contribution to the proof of the famous Sendov's conjecture. Thank you very much, Professor Tao, for accepting our invitation. Thank you. Now I will give the floor to three mathematicians, one physicist, and one charming policymaker to say a few words in memory of Academician Sendov. Academician Kenderov, you have the floor, please.
Thank you, Oleg. Blagovest Sendov was a unique person. We, his students, colleagues, and friends, admire him not only for his mathematical contributions and for building up the approximation theory school in Bulgaria, but also for what he did for the entire Bulgarian mathematical community and for the whole society. I'll list only three things. 25 years ago, before continental Europe accepted the three-level university education with bachelor, master, and doctor degree, Sendov introduced and implemented this system in the Bulgarian mathematics and informatics education, which was quite unusual in those times. As early as the beginning of 80s last century, Sendov had the vision for the use of computers in education and conducted a large-scale school experiment with style of teaching and learning based on inquiry and understanding, which was also very novel in those times. Well before the democratization of the political life in 1989, he introduced the so-called grant system for funding research projects. For the first time, a large group of projects leaders got the right and simultaneously the responsibility to operate with financial and other resources. This was a democratization of Bulgarian science in the sense that a large group of people was granted the right to make decisions. Last but not least, it doesn't happen very often to have around somebody who, at different stages of life, was president of the largest educational institution in Bulgaria, Sofia University, president of the largest research institution in Bulgaria, Bulgarian Academy of Sciences, president of the National Parliament, ambassador of Bulgaria in Japan, and a key person in several international organizations. The expertise and wisdom he had will be a good pattern to follow for the generations to come. Thank you.
Thank you, Academician Kenderov. Now we will hear Academician Ivan Todorov, who is presently in Paris and who sent us recording.
Благовест Сендов was an aspiring young mathematician, aged 26, when he made his conjecture. At 87, he was enthusiastic. He was the Bulgarian soul of the then projected International Center for Mathematical Sciences. We are fortunate to have Terence Tao, a bright star in the world of mathematics, to speak today about Sendov's conjecture. I believe that Blago would have been glad to observe this event from somewhere.
Our gratitude to Academician Todorov, and now I pass the baton to Professor Lyudmil Katsarkov, who is the scientific director of our International Center. Please, Lyudmil.
All right, thank you, Oleg. Yeah, I met Academician Sendov when we started working on the creation of International Center for Mathematical Sciences in Sofia. And in fact, it was suggested to me to work with him by Sir Michael Atiyah. And so the way Atiyah introduced Blagoev's Sendov to me was as follows. He said, you really have a huge help down in Sofia. In fact, in Bulgaria, you have the greatest politician among mathematicians. And I actually decided to tease Atiyah and ask him better than Hirzebruch. And Atiyah said, well, it's easy to be a politician in Germany, and it's much harder to be a politician in Eastern Europe, where everyone is ready to stab you in the back. That's what Atiyah said. But in any case, his suggestion was really a great one, and the center was created. And at the very beginning, Academician Sendov was able to arrange some deals with some American institutions. And so I would like to give the opportunity to the director of IMSA in Miami, who has arranged some deal with Academician Sendov, to say a couple of words about it. Steve?
Thank you, Lyudmil. Welcome to everyone from today's sunny Miami. I'm delighted to be here at this event and to say just a few short words. I was very fortunate to get to meet Academician Sendov in September of 2019 when we were having the formal event starting our new Institute of the Mathematical Sciences of the Americas, which we are hoping to have be not only a force for advancement in mathematics and its applications across the Americas, but also globally. And as part of that, and in no small part as a result of some of the discussions and dinners that I had with Professor Sendov while he was here, we began working on a what we're calling the IMSA consortium, of which the ICMS is a charter member. And in fact, our collaboration, we hope, expect next year to have a jointly mentored postdoctoral scholar spending the part of time here in Miami and then also in Sofia. we're very excited about that prospect, and I expect that Academician Sindorf would be very happy about that. Thank you very much.
Thank you, Steve. And I would like to give the opportunity to Professor Philip Griffiths, one of the most notorious and most famous geometers of 20th and 21st century, Director Emeritus of Institute for Advanced Studies in Princeton, to say a couple of words about Academician Sendorf. Philip?
Thank you, Ludmil. Sendorf was one of the leading mathematicians in the Balkans. I think to me especially impressive was the very broad view he had of mathematics. Very specific problems dealing with zeros of polynomials, mathematical biology, all the way to computer science. Also, I think very impressive and very important was, as was mentioned earlier, the substantial school of students that he was instrumental in helping to establish. We met here in Miami, as Steve said, at the opening of IMSA, the inaugural event, and I found a lot in common with Academician Sendorf. We met both professionally and socially, and it was a great pleasure on both counts. It's clear that he has had immense experience and as organizing science and has proven leadership. We discussed the collaboration that Steve mentioned between IMSA here in Miami and ICMS in Sofia, and I'm delighted to see that this is progressing very nicely. So again, it's a fact that we are now, I think, collaborating institutions, organizations, and we look forward to a very promising future of this collaboration. Thank you.
Thank you, Philip. And I would like to introduce Minister Karina Angelieva, who would like to say a couple of words about Academician Sendorf. Karina?
Hi, everyone. Thanks really for this invitation. It's a great pleasure to be with you. Can you hear me first?
Yep.
Okay, thanks. Thank you very much. It's really a great honor for me, and maybe I'm the only one not mathematician probably today to join this great event. To share my memories of Academician Sendorf. Maybe you'll be surprised, but I met him only 2 years ago. When we start to work together and to discuss reforms that are needed in the research and innovation sector in Bulgaria. And as Professor Katsarkov already said, we start this ambitious goal to establish International Center of Mathematics in Bulgaria. But basically, the name of the Academician Sendorf followed my wife, because already in primary school, I was the first generation of kids to enter into a pilot school, modeling his new approach on education. It was called the Sendorf System on Education, and I was very lucky because I was not even supposed to write with pencil, but already in the first year in school, I was using a computer. Later, unfortunately, this system was not largely scaled, and now in the COVID times, all the discussions for changes necessary in the education system also revoke these ideas that Sendorf already was doing it, basically, not only talking about them. You can imagine how many years ago. And of course, in this now honorable group of very famous people, that remind ourselves that Academician Sendorf also was a great person to work for the image of Bulgaria, no matter that we were at some point of in the communism system, but he was a great ambassador to Japan, and overall, I must say, he was a great science diplomat all over the world. So these are my memories. I really regret that we couldn't finalize with him one reform we started. But I'm still inspired from him, and I'm following his approach to work with young people. So my ambition is really to support the young generation of people to follow a career in mathematics and to develop their talents. So this is for me, academician Sendov, and now here in my library, I have one book he gave me in December 2019, 1 month before he died. The book is called "The Democracy is Like the Moss. The democracy don't grow somewhere where there is the right environment and the seeds for this." And I think this I will remember, and I will follow in all my activities. So great news from Terence Tao that he solved this problem. I'm very intrigued to follow this event. Thank you very much, Lucy.
Thank you. All right, I think it's time to move now to the star of the show, Professor Terence Tao. Let me say a couple of words. Of course, he's very famous, but for people who haven't heard that, Terence Tao is one of the most prolific mathematicians of our times, and so he covers a lot of very broad spectrum of mathematical areas, from harmonic analysis to combinatorics, and from number theory to partial differential equations. I mean, he is rightfully compared to Mozart of mathematics because of the beauty and elegance of his proofs, who are just divine. And so let me let on you Professor Terence Tao from UCLA, who is going to tell us about his recent approach to Sendov's conjecture for zeros of polynomials. Terry? Let me just briefly say that if you have any questions, you can put this into the, to send this either to Velichka Milusheva or just put them in the chat as a question. Thank you. Terry?
Okay, thank you very much. It's a great honor to speak at this event in honor of academician Sendov. I never unfortunately met Sendov, but he was learning about how remarkable a person was. I really regret the opportunity to meet, and I've never actually been to Bulgaria, but I guess now I am at least virtually visiting, so that is very nice. So I don't remember when I first learned about this conjecture, maybe as a graduate student or as a postdoc. I heard about his famous conjecture in passing, but it wasn't my area. I never really worked in polynomials when I was younger. It's only recently, in the last few years, that I happened to work in the study of random polynomials with random coefficients and the distribution of their zeros. But even then, I didn't make the connection to this conjecture that ideas from probability might be relevant. It was only actually in the last few months when I was preparing a graduate course on complex analysis, that I actually came across the conjecture again and realized actually that some of the new techniques in the theory of random polynomials could be used to help attack this conjecture, at least asymptotically. I think it's a great demonstration of the unity of mathematics, that all areas of mathematics are connected. And so in particular, you will see ideas from probability come in this talk, even though there was no probability initially in Sendov's conjecture. So Sendov's conjecture is one of the basic open questions remaining about polynomials of one variable. So if you have a polynomial, let's call it f of z, of degree n, in one complex variable z, we have, of course, the fundamental, this is already a typo, fundamental theorem of algebra, not fundamental theorem of calculus. The fundamental theorem of algebra says that any such polynomial has got n zeros, lambda 1 to lambda n, And in this talk, I will consistently try to color zeros in red and critical points in blue. We have n zeros, possibly repeated, so there could be multiplicity, and I'll call them lambda 1 to lambda n. And then there are also some critical points. Critical points are stationary points of your polynomial, or zeros of the derivative. And the derivative has degree n minus 1. So there's n minus 1 critical points, and I'm going to call them zeta 1 to zeta n minus 1. These zeros, or critical points, determine the polynomial up to a constant. So it's traditional to normalize the polynomial to be monic, which means the leading coefficient is 1. So you can write any polynomial f as the product of n linear factors depending on the zeros, and the derivative is also a product of n minus 1 linear factors depending on the critical points, and there's also a constant of n at the front. And a basic question in the subject is, what is the relationship between the zeros of a polynomial and the critical points? These are the two most important features of a polynomial often. And so how are they related? So there are many, many relationships between them. So first of all, if you actually do numerics and you plot polynomials on computers, you see that there really should be a relationship. So here's a picture from actually two other mathematicians, Klaputro and Seidel, who are working in this random polynomial literature. So what they did here is that they took the unit disk, the disk of radius 1, and they selected 1,000 points at random, and these are these blue points. Red points actually. You can't see the red points, most of them, because they're actually hidden by the blue points. But they selected 1,000 red points in the disk at random, and then they formed the polynomial with those of degree 1,000 with those points as zeros. So you just multiply together 1,000 linear factors, and you get this polynomial. And then you take its derivative, and you compute the zeros of that. Those are the critical points. So there's 999 critical points, and those are in blue. And what you find is that the 999 critical points are very, very close in location to the 1,000 zeros. I mean, so much so that you can't even see most of the zeros in this picture because they're hidden by the critical points. So there's clearly some relationship, at least on the level of random polynomials. Now, if you worked with real polynomials, with real zeros, rather than complex polynomials, then of course we have an extremely classical theorem that we teach to first-year undergraduates about the relationship between zeros and critical points. And that's Rayleigh's theorem, that when your zeros are real, then between any two real zeros, you have a real critical point. Okay, so the n minus 1 critical points are said to interlace the zeros. So so here we have 3 zeros and 2 critical points, and the 2 critical points just lie between the 3 zeros. So the relationship is very simple, but that's only in the case of real zeros. It doesn't work for complex zeros. And I understand actually that one of Sandow's motivations in his conjecture was to try to understand what would be a complex variable analog of Rayleigh's theorem. For complex zeros, the most famous result we have is the classical Gauss-Lucas theorem. So there is a basic relationship between the zeros and the critical points, which is that the critical points lie in the convex hull of the zero. So you find the smallest convex polygon that contains the zeros, and that also contains the critical points. And this is something that you can prove to an undergraduate complex analysis class. If you start from factoring your function f as the product of linear factors depending on zeros, you can take the logarithmic derivative, and you get this identity, that the ratio between the derivative and f is just the sum of all these factors coming from zeros. And at a critical point, the left-hand side is 0. So there is a basic identity relating the critical points. Every critical point solves this equation, that the sum of the reciprocals of the critical point minus all the zeros sums to 0. And using that in just a little bit of complex geometry, you can get the Gauss-Lucas theorem. Okay. So here is just a schematic depiction of the situation. The zeros are in red, and so if you have a certain number of zeros, the critical points are forced to lie inside the convex hull of the zeros. So that's one relationship between zeros and critical points. It's not the only relationship. Here's another basic relationship. If you take all the critical points and you take their average, so you sum them up and you divide by n-1, that happens to be the same as the if you take the zeros and sum them up and take the mean. Okay, so they have the same mean. Actually, this is already the first hint that probability might be useful, since expectations and means are so basic to probability. But okay, but this is a very easy fact. Basically, you just take the two formulas that you have, that the polynomial f is a product of factors coming from the zeros, and the derivative is a product coming from the critical points, and you just expand out both products, and you look at the first two terms, and you very quickly see that indeed the two things have to match. All right, so that's another fact. Here is a less well-known fact, but quite nice. There was a theorem called the perpendicular bisector theorem, proved by Szegel back in 1922, which I'll state in the following slightly strange way: that if you have two zeros, I'll call them lambda 1 and lambda 2, and you form the perpendicular bisector. So you take the midpoint and you take the line perpendicular to the midpoint between them. That's called the perpendicular bisector of these two zeros. Then the critical points can't all lie on one side of this bisector. They have to either lie on both sides. There's some critical points on one side, some critical points on another side, or maybe some of them lie on the line itself, on the bisector itself. But they can't all lie on one side. So there's a separate constraint between zeros and polynomial zeros and critical points, which is not covered by the Gauss-Lucas theorem. That follows, by the way, from a very deep theorem of Grace, proven in 1900, which is a relationship between any two polynomials. That if you have any two polynomials of the same degree, f and g, and if all the zeros of one polynomial f lie on one side of a line or one side of a circle, and all the zeros of the other polynomial lie on the other side, then the two polynomials have to be related. There's a certain inner product between those polynomials called the polar form, which is some combination of the derivatives of f and the derivatives of g. And when these polynomials are so different that they lie on different sides of a circle or different sides of a line, then this inner product has to be non-zero. And you can use that to prove Zegel's theorem as a corollary. I won't do that here. Okay, oops. So this is just an example of what cannot happen. Okay, so if you have two zeros, which are these two red points, you get this perpendicular bisector, which is this vertical line, and you cannot have all the critical points lie on one side of this line. That's another relation. So Sendov's conjecture, which he made in the 1950s, is another conjectured relationship between the zeros and the critical points. So if the critical points, so if the zeros all lie in a disk, say the unit disk, like I showed in this first example with this random situation, then all the critical points have to lie close to the zeros. Now, in the picture I showed earlier, the critical points were actually lying very close to the zeros, but here close, actually the correct notion of closeness is unit distance. That if you take any zero, every zero in the unit disk has to have a friend, has to have a critical point which lies within a distance 1 of the zero. So if you have a zero called A, then there has to be a critical point within the disk of radius 1 centered at A. Oops. So this zero can lie anywhere in the disk. It's traditional to rotate the disk so that the zero lies in the positive real axis, so on the unit interval between 0 and 1. That's the convention. Okay. So here is a picture of what Sendov's conjecture says does not happen. Okay, so this is a situation which should not happen. Here, the left circle is the unit disk, and all the zeros, which are the red points, lie in the unit disk. And then among those zeros, there's a special zero that we call A, and I'm placing on the real axis, which is not drawn here. And then there's a separate disk of radius 1 around A, and what should not happen is that all the critical points, which are the blue points, stay outside this disk, and they only lie in this crescent here, which is the shape is called a lune. Okay, but the situation where there's no zeros in this right disk is not actually, it should be prohibited. This is what the conjecture says. Okay. Why distance 1? Okay, so why is this unit distance the right distance? Well, there are examples that show that this statement is basically the best statement you could make of this type regarding the separation between zeros and critical points. So there are two basic examples, depending on where you want this special zero a to be. So there's an example near the origin where a is actually at 0. So a very simple example of a polynomial of degree n is z to the n minus z. Okay, that is a polynomial of degree n. What are the zeros? Well, if you look at it, there's a 0 at 0, so there's a 0 at the origin. But then there's also n minus 1 other zeros, and you factor out z, you see that the other zeros are just the roots of unity. There are certain roots of unity on the unit circle. If you differentiate this polynomial, you get n z n minus 1, and you can compute the zeros, the critical points. Critical points they're almost roots of unity. They're roots of unity minus a small factor, sorry, times a small factor, n to the minus 1 of n minus 1. And that's a factor which is almost 1 when n is large. And so the critical points almost lie in the unit circle. So I have a picture here. So in this particular example, the zeros, which are in red, consist of the origin, which we call A, and then some points on the circle. So all the zeros lie in the unit disk, and the critical points do lie in the disk of radius 1, centered at A, but they only barely do. They're pretty close to actually escaping this disk. So if we were to replace the disk of radius 1 by any smaller disk, the conjecture would be false, at least for n large enough. Okay, so that's one example. Another example where now the special zero is on the boundary of the circle rather than the center. So now we take the polynomial z to the n minus 1. And so now the zeros are the roots of unity, the nth roots of unity. So they all lie on the unit circle. And among them, among those zeros is the 0, 1, which that's going to be our special zero a. The critical points, so the derivative of f is n times z to the n minus 1. So you have a zero of big multiplicity, a critical point of order n minus 1 at the origin. So there's all the critical points are at the origin. And again, in this case, Sundow's conjecture is true, but only barely true. It is just on the border of being false. So here is the picture now. The polynomial, the zeros of the polynomial all lie on the boundary of the unit disk. These are these red points, and then the special zero a is at the location 1. And all the critical points with a huge multiplicity are the origin, so that's why I've drawn by this big blue circle. And the critical points, they barely lie in the unit disk centered at A. So if you were to shrink the disk by any smaller disk, the conjecture would be false. So here the critical points have almost escaped the disk of radius 1 centered at A, but not quite. They reach the boundary, but that's it. So in fact, it's conjectured by Rodriguez and Phelps that this is basically the only way in which Sundow's conjecture can even come close to failing. So the only way that the critical points can almost escape the disk, it's believed, is this example or slight variance of this example. You can rotate this example and you can multiply your polynomial by constant, but basically this is the only picture where Sundow's conjecture should come close to failing. Okay, so there's been a lot of work on the conjecture. At least 100 papers, actually. I don't know the full literature. For any fixed degree, like if I pick a degree like 17, this is a statement about polynomials of degree 17, so that's like 18 complex numbers. It's a finite sentence in first order arithmetic over the complexes or the reals, actually the reals. And so there's a general theorem Tarski that says that such statements are decidable. So in principle, if you had a very powerful computer, for any degree n, you could use a computer to decide whether the conjecture is true or not. Although in practice, the time needed to verify the conjecture for a given n grows at least exponentially in n. So this is not a practical way to resolve the conjecture for any fixed n, except for very, very small n. And in fact, the conjecture has only been verified for quite small values of n. So in this slide, you see over the years, people have verified the conjecture for degree. So the first case is 2. 1 is degenerate. There's no critical points when n is 1. But for all n up to 8, we definitely have the conjecture verified. There have been papers claiming 9 and 10, but they haven't really been verified, I think, or accepted by others in the literature. And in fact, actually, there are multiple attempts to prove this conjecture, which are claimed and then retracted. I think there was even one last year. I think it's like any other conjecture which is famous and fairly easy to state, is that it really attracts a lot of attempts, most of which unfortunately don't work out. Okay, so that's what happens for small n. What happens for big N, large N? There are some results for large N. So for example, there is a result of Bozhanov, Raman, and Sati that shows that if you make the disk that traps the critical points just a little bit larger, so instead of the disk of radius 1, you take the disk of radius 2 to the 1 over n, the nth root of 2. Then the conjecture is true. So given any 0a, there is a critical point which lies not within 1 of a, that would be Semmel's conjecture, but within 2 to the 1 over n, which is only a little bit bigger than n, and as n gets larger, 2 to the 1 over n converges to 1. So in some sense, Bozhanov, Raman, and Sati somehow show that Semmel's conjecture becomes almost true in the limit when n is big. This is already a hint that maybe the high degree case is actually easier than the low degree case, despite the fact that much of the progress before was for low degree. And there are other results that have been established for large n, but previous results had to make additional assumptions on the location of the special 0a. So there are basically 3 cases, depending on whether a is near the origin, a is near the circle, or a is somewhere in between. So I just want to summarize some of the previous results that have been done on this conjecture. Okay. So first of all, I mentioned the Gauss-Lucas theorem. So one immediate consequence of the Gauss-Lucas theorem is that the conjecture is true if your special 0 is at 0. Okay, so if a is at 0, then this disk of radius 1 as centered to a is the same as the unit disk, and the unit disk is already convex. So if all the zeros are inside the unit disk, then of course all the critical points are inside the unit disk as well. So the conjecture is true at 0. In 2011, Bozhanov discovered a slightly improved version of the Gauss-Lucas theorem, which I won't state here, but you can actually shrink a little bit the set where the critical points live, not just the convex hull of the zeros, and he was able to stretch this argument and cover a small range of a around 0. So all a between 0 and 1 over n minus 1, he was able to verify the conjecture in this case by a strengthened version of the Gauss-Lucas theorem. Okay, so this is that's the results that are known for a near 1. When a is near 0, there were several authors, Rubinstein, Goodman, Raman, Ratti, and Joyal, who showed that Semmel's conjecture is true when a is equal to 1. So if the special 0 is actually on the circle, which was in the case in our second example, then they were able to show that Semmel's conjecture is true. And then people were able to perturb this result a little bit. I think Miller and Văceatu-Sărescu were the first to show that you could actually also show that a is true for some, the conjecture is true when a is in a sufficiently small neighborhood of 1, where sufficiently small depends on n. The neighborhood gets smaller as n gets larger. And then later, people found an explicit range of the neighborhood. And quite recently, actually 2014, the best range we have is by Kazmauka, which gave a region of size about 1 over n to the 12th. That there's a small neighborhood around 1 where the conjecture is also verified. Okay, so we have those 2 extreme cases. Okay. Unfortunately, you can't interpolate. There is no sort of convexity that allows you to then get all the intermediate cases. Then there are some results for a in between 0 and 1. So Degas had a very nice paper, which was actually a lot of which inspired my own work actually. And he used, in particular, this perpendicular bisector theorem that I mentioned previously of Zegel, and lots of nice elementary inequalities to relate zeros and critical points. And what he showed is that if your special 0A is far away from 0 and far away from 1, so if it's bigger than some constant c and less than some constant 1 minus c for some small c, let's say 0.1, so if A is between, say, 0.1 and 0.9, then he was able to prove Sandow's conjecture, but only assuming that n is sufficiently large. So only assuming that n is really big compared to this c. Okay. So he was able to establish a result for n large enough if you stay away from 0 and 1. And it was only last year, actually, that so in Degas' analysis, he did not specify exactly how A and C were related. But this was carefully done by Chalebgois just last year. So you can see this has been a quite active area of research. And so he actually gave an explicit bound on how large n has to be for Degas' argument to work. It has to be quite large. So this quantity here, actually, I think it never gets smaller than 2 million. And it often actually is much larger than that. As if your 0 gets close to A or 0 or 1, then actually this bound goes to infinity. But basically what this result does is that it verifies Sandow's conjecture for an intermediate range. So there's some large constant c, such that if your 0 lies between a constant multiple of n to the minus 1/7 and a constant multiple of n to the minus 1/4, 1 minus that, then the conjecture is also true. So we have these 3 separate regions where the conjecture is known to be true, and this works for even very large n. But unfortunately, there are these gaps, and that when n is large, there are some significant gaps between these 3 results, which are proven by 3 very different techniques, by the way. So there are these 2 missing gaps that that still needed to be handled. One is when the 0A is close, but not too close to 0 in this following precise sense, and also when A is close, but not too close to 1 in this other precise sense. So these were the 2 remaining regions. It is a little strange to have a situation where the 2 difficult cases are in sort of very different extremes of your domain, but that's just what happened. All right. So what I was able to do, so I still have not resolved the full conjecture, and I don't think actually my methods do, you have to use some new ideas to resolve the full conjecture. But what I showed is that there is some constant degree n naught. I don't tell you what it is, but there is a constant n naught, above which the conjecture is true regardless of what A is. So as long as your degree is big enough, the conjecture is true. Right, so I can fill in these remaining gaps in the large n literature, but only asymptotically, only when the degree is big enough. So in principle, this means there's only a finite amount of work left to resolve the conjecture. So first you have to work out what n naught is. Now I don't do this. In fact, it's a little bit difficult to actually extract an explicit value of n naught from my argument because I use compactness methods, and compactness methods are notorious for not producing explicit constants. But I believe if you worked hard enough, you could actually get a constant, but it would be massive, it would be in the billions at least. And we don't have the ability to verify the remaining cases of the conjecture in any reasonable amount of time. I mean, it'll be finite, but it'll be like exponential in the degree or something, which is not feasible. So there's still work to be done, but but at least the asymptotic case where n is extremely large is actually solvable. So that's perhaps a surprise to those who work. I mean, that's maybe the takeaway is that actually the problem gets easier as the degree gets bigger, once the degree gets very, very big. So as I said, it uses a compactness method, the argument, and it's a method which I like to call compactness and contradiction. It's very popular in other areas of mathematics, particularly PTE, which is where I learned it. It's a style of argument which takes some getting used to. I mean, it uses proof by contradiction, which is always a difficult concept to explain to undergraduate students, for instance, that you're trying to prove something is true and you assume it's false, and this is always very counterintuitive. So, but that's what we do here. To prove this conjecture asymptotically, we assume that it's false. We assume that it is not true asymptotically. And what that means is that there must exist arbitrarily high degree counterexamples to Sandler's conjecture, that there's some sequence of degrees going up to infinity, and there's some sequence of polynomials whose degree is getting bigger and bigger, and there's some special zeros, A, which is moving around the unit disk, and for each of these polynomials, the conjecture is false. Okay, that the critical points stay away from the disk centered at the zero. So what you do is that you try to exploit compactness somehow. So the set of all polynomials in the world is not compact, but you somehow try to find something which is compact. So you have to replace the polynomial by some other object which does live in a compact set. And this is where ideas from probability start becoming useful. And you try to create some limiting object. What is the you show that after passing to some subsequence, perhaps these polynomials converge to a limit as the degree goes to infinity. But this limit will probably not be a polynomial. You have to understand what this limit is, and then you try to say as much as you can about it. And it turns out that the limit is a very nice object. It's actually a pair of two random variables. And you can analyze it using some tools that are only available in this asymptotic regime. And one tool that we rely on in particular is the unique continuation of harmonic functions or holomorphic functions. That if two holomorphic functions say agree on a small set, you can continue that, and they will agree on a bigger set as well. And you can understand the asymptotic limit very, very well, and then you try to go back to the finite world and understand what this tells you about the examples, the original counterexamples, to control where the zeros are and where the critical points are. All right, so let's see how this works. Okay, so first let's talk about arguing by contradiction. Okay, so as I said, if Sandler's conjecture is not true for asymptotically in the asymptotic limit, then there must be a sequence of degrees n going up to infinity, and for each n in the sequence, there must be some counterexample polynomial f, which we can make mnemonic, and it has some zeros, and there'll be more and more zeros as the degree gets bigger. So there'll be n zeros, lambda, all in the unit disk, and there will be one special zero among them, which we are placing on the unit interval between 0 and 1. And these polynomials have the property that they refute Sandler's conjecture, that there is a disk of radius 1 around disk A, and all the zeros avoid this disk. Okay, so they avoid the disk centered at A, but they have to lie in the disk centered at the origin because of the Gauss-Lucas theorem. So the zeros lie in the unit disk, and the critical points lie in the convex hull of the zeros, so the critical points must also lie in the disk. So the critical points must lie in this Lune region. It's inside one disk and outside the other. And we need to show that this situation leads to a contradiction when n is large enough. Okay, so the picture is as follows. The zeros, so we have many zeros now. We have many red points in the disk of centered at the origin, including this special zero at A. And then we have many critical points, but the critical points are all deciding to lie over here. So this is a very different picture from the first picture I showed for random polynomials, where the zeros and critical points were almost sitting on top of each other. But here, the critical points are deciding to live only in this Lune, and the zeros are spread out everywhere, including at this one point A. And this situation is supposed to lead to a contradiction. Okay, so now we have the sequence, and we want to say that because of compactness, there should be some way to take a limit as n goes to infinity. So what do we have? We have our polynomials f, and we have the special zero a, and we want to extract a limit as n goes to infinity. So in the case of the special zero, this is very easy because we have the very basic theorem in real analysis, which we teach to undergraduates, which is the Bolzano-Weierstrass theorem. So the Bolzano-Weierstrass theorem says that if you take a sequence of real numbers in a compact interval like 0, 1, then you can pass to a subsequence, and in the subsequence, you can make this sequence converge to a limit. So all so this special zero, it can move around between 0 and 1, but we can pass to a subsequence, and we can make it converge to a limit, which I'm going to call A infinity. And so our special zero is equal to our limiting zero plus something which goes to 0, when I'm going to call that little O of 1. Okay. And this now lets us split into the 3 cases that we've seen in previous work. So this limiting value is somewhere in the unit interval. So it could be 0, it could be 1, or it could be in between. So maybe the limiting value is 0. So that means that our special 0A is little of 1. It's not 0 necessarily, but it converges to 0. Or maybe our limiting A is 1, in which case the finite A is 1 minus little of 1. It converges to 1. Or A is, or the limit value is strictly between 0 and 1. So then A will be bounded from above and below by some constant, and 1 minus that constant up to some little O1 errors. Okay, but the third case we don't need to worry about, because this previous result of Degoe actually shows that this case is not possible for n large enough. So actually, the only 2 cases we need to consider remaining are one where the limiting value is 0 and one where the limiting value is 1. And that's just rephrasing something I said in a previous slide. Okay, so in those 2 cases, we need to show that there's a contradiction. Okay, so that's what I was able to do. So in my paper, I have 2 separate theorems. So I introduced 2 more ranges, which combined with the previous results that were known on this problem, we were able to cover all the possible ranges of A and then rule out completely resolve Sedlov's conjecture asymptotically. So firstly, I was able to show that if A is close enough to the origin, and for me, close is that A goes to 0 faster than 1 over log n, little over 1 over log n. So in this region between 0 and something small times 1 over log n, for example, 1 over log n squared, then we can get a contradiction. And that covers the missing gap between 1 over n minus 1 and constant n to 1 minus 1 over 7 if n is big enough. And then the other result I showed is that if A goes to 1, so it's 1 minus something goes to 1, but it doesn't go to 1 too fast. That it's less than 1 minus a small constant to the n, and this can be any small constant. So as long as it's not exponentially close to n, but to 1, but it does converge to 1, then I can also get a contradiction, and that covers the remaining range. Okay, so my 2 results together with 3 previous results in the literature. Actually, I guess maybe you don't need this one. Maybe just 2 previous results in the literature cover the remaining cases. Actually, the methods that I have can also reprove some of the previous results too. So I could also get a self-contained proof, but it's shorter to just use the previous literature. Okay, so as I said, the whole strategy is to take a limit as n goes to infinity. So we have a sequence of polynomials, and we ask what is the limit of this polynomials? Now, in analysis, of course, we teach there are many ways to take limits of functions. There's pointwise convergence, there's uniform convergence, convergence in measure, so on and so forth. These don't work very well for these polynomials. The limits that you get are kind of boring. I mean, they're either 0 or infinity or undefined. So just to give one example, you take this sequence of polynomials, z to the n minus 1, and you ask, what is the limit of this as n goes to infinity? What do these polynomials look like? Well, if z is small, if z is inside the unit disk, z then goes to 0, and this polynomial just converts pointwise to minus 1. If z is bigger than 1, if it's outside the disk, this polynomial is just diverged. They'd have no limit. Goes to infinity. And on the circle, if z is on the circle, it oscillates. It doesn't go to infinity, it doesn't go to any other finite limit. It just goes round and round. Except maybe when z is 1, when it goes to 0. So the limit is not very interesting. It's just like minus 1 inside the disk, infinity outside the disk, and undefined on the disk. So it's not the polynomial itself that you want to take limits of, because you don't get much information. What you want to do is you actually want to take the limits of the zeros and the critical points. But here we have the problem that the zeros the zeros, the size of the number of zeros, the number of critical ones is going to infinity. It's not just 1 point or 2 points. You have more and more points as the degree goes to infinity. So the idea is not to think of the zeros individually, but to combine them into a single object. And here's where the perspective of probability theory becomes useful. You should not think of individual zeros or individual critical points, but you should think of a random zero and a random critical point. And these are random variables. And it's the random variables that have useful limits. So here what we do, okay, so for any fixed degree n, we have a polynomial f, we have n zeros, which we call lambda, and we have n critical points. And you just pick a zero at random. And this is a random variable, taking one of n different values, and each zero has probably 1 over n of being selected. If there's multiplicity, then of course that zero will have a higher probability of being selected. So I'll just call this red lambda with no subscript or superscript. That's a random zero of f. And similarly, I will pick a random critical point, which I call zeta, out of all the n-1 possible critical points. Okay, and we can choose these to be independent random variables. Okay, so we have these two random variables which you can associate to every single polynomial. Okay, so for instance, if f is this polynomial, zeta n-1, then all the zeros of this polynomial are n through the unity. So lambda is just a random n through the unity. So it is the n through the unity spread around the unit circle, and you just pick one at random, and that's lambda. Here, all the critical points are at 0. So in this particular case, zeta is actually not random at all. It's actually, this is one of the few cases where zeta is actually still deterministic. It is always 0, because all the critical points in this case are 0. Okay, so that's an example. In this other example, zeta n minus z, then the random zero, it can be 0, but not very often, only probably 1 over n. But almost always, what's going to happen is that this random zero, is going to be a root of unity. It's going to be spread somewhere on the unit circle. And zeta is also a random root of unity times a small factor, n to the minus 1 over n. Okay, so we have these two random variables. Lambda, the random zero, that's going to be some random point in the unit disk. And zeta is going to be a random point in this lune. It's also in this disk of center at the origin, but it avoids the disk center at A. Okay, so why do we introduce these two random variables? It's because there is another notion of convergence, which probability theorists use, probabilists use. So beyond pointwise and uniform convergence and so forth, there's a notion of convergence in distribution. That if you have a sequence of random variables like Cn, and we say that such a sequence of random variables converges in distribution to another random variable, which I call skew infinity. If whenever you take a test function, phi, okay, this is a typo, it shouldn't be f, it should be phi. If you take a test function, a bounded continuous function, and you apply a test function to your random variables Cn, the expectation of any such test should converge to the expectation of the limiting random variable. This is what it means to convergent distribution. It implies, if your random variables are bounded, it implies, for instance, that the means of Zn converges to the means of C infinity, the variance converges, all the moments converge, and things like that. So it's a very common notion of convergence that is used in probability, and the reason why it's useful is because of this famous theorem of Prokhorov, that I don't actually know if he's Bulgarian, but anyway, but Prokhorov's theorem is that if you have any sequence of random variables, of bounded random variables, there is always a subsequence that converges in the distribution. So it's like a random form of the Bolzano-Weierstrass theorem. Okay, Bolzano-Weierstrass says that any bounded sequence of deterministic complex numbers has a subsequence that converges, but any random sequence also has a subsequence that converges, but only in distribution. It's a fairly weak notion of convergence. Okay, but it is a compactness theorem, and we can use it. So we can pass to a subsequence, and so our random zero lambda we can pass to a subsequence, and we can assume that this random zero converges in distribution to a limiting random variable, which I call lambda infinity. So these distributions converge to some random variable. And similarly, you can pass to an even further smaller subsequence, and you can assume that this critical point, this random critical point, zeta, also converges in distribution to some limiting random variable zeta infinity. So our limiting object is not a polynomial, but these two random variables, lambda infinity and zeta infinity, are in some sense describing what happens asymptotically. Okay, and they're related to your original random variables. For example, all the moments of your original random variables converge to the moments of these limiting random variables. All right, and the reason we do this is because the limiting random variables behave better. They are simpler and nicer and have better properties than the original random variables. Okay, so for instance, if I look at our two examples, okay, so if f is C minus 1, in this example, lambda is a random nth order unity, which is a discrete distribution on the unit circle. But in the limit, it will converge to the uniform, the continuous distribution on the unit circle. It will be in the limit, the limiting 0, lambda infinity, will be uniformly distributed on the unit circle. The critical points, they were all 0, and so the limit will also all be 0. Will just be 0. Okay, so in this example, the asymptotic 0 is just uniformly distributed on the unit circle, and the asymptotic critical point is always at the origin. Then our second example, z and minus z, lambda, the random 0, it can be 0, but not very often. It's only 0 with probably 1 over n. So asymptotically, actually, it's never 0. Or it's an nth order unity, n minus first order unity. So in the limit, lambda infinity will just be uniformly distributed on the unit circle. You will, the limit will forget about the 0 at 0 and only remember the zeros on the unit circle. Zeta, in this case, is an order unity times a constant, but this constant goes to 1 as n goes to infinity. So the random critical point is also uniformly distributed on the unit circle. So even though the critical points and zeros are different for finite n, in the limit as n goes to infinity, in some sense, the critical points and the zeros converge to the same thing. Okay, so here I just drew a very schematic diagram. So in the first example, the zeros are in the limit. The zeros are uniformly distributed on the unit circle. So I've depicted that by this sort of irregular smear on the unit circle. This is my notation for a probability distribution. Whereas the critical points, they're all sitting at the origin. So this is what the two limiting objects look like when you take the limit of z to n minus 1. And A is converging to the point at 1. And if instead you take z to n minus z, then the special 0 converges to 0. So A is at 0. But the critical points and the zeros, their limiting distribution, they're just both uniformly distributed on the unit circle. So that's the other picture that shows up in our two examples. Okay, so these two random variables are very connected to the polynomial f. So I came at this problem from the random polynomials literature, and it turns out that all the progress, well, a lot of the progress on random polynomials comes from trying to relate the polynomial to these random zeros and random critical points using potential theory, actually. Remember the original polynomial f is related to these. It's a product of terms related to the zeros. So one way to exploit this identity is to take logarithms to turn this product into a sum, and then you can divide by n, so you can turn the sum into a mean. You can also take reciprocals as convenient, and so you can arrive at this identity that if you take this normalized logarithm of the function f, so you take f absolute value reciprocal log divided by 1 over n. So this expression is what's called the logarithmic potential of the random 0 zeta. So you take zeta and you take the log of 1 over the distance between z and zeta for any z, and you take the expected logarithmic distance to a random 0, and that's some function of z. This has a name. It's called the logarithmic potential of lambda, and I'll call it u lambda of z. So it's a basic object that's studied in potential theory. And so what we see is that the logarithmic potential of the random zero tells you it controls the magnitude of the tells you how big the polynomial is. That the magnitude of the polynomial is controlled by the log potential of z. But you have to normalize the magnitude first before you see the relationship. Okay. And there's a very similar relationship. The log potential of the critical points controls the magnitude of the derivative. So the so lambda tells you how big f is, and zeta tells you how big f prime is. There's another identity that's also very important. If you take, again, this factorization, if you take the logarithmic derivative, so you take log and then differentiate, or equivalent, if you take f prime over f, that also converts this product into a sum. And if you normalize it divided by n, you see that the normalized log derivative is actually the expected value of 1 over z minus lambda. And this also is a well-studied object. This is called the Cauchy-Stokes transform of lambda, and I'll denote it S lambda of z. So there's another transform of lambda, and this other transform of lambda controls the logarithmic derivative of f. So it controls the ratio between f prime and f. And similarly, the log derivative of zeta, the random critical point, controls the ratio between f prime prime and f prime. So we get these very useful identities. This is important because in the limit, as n goes to infinity, lambda converges in distribution to lambda infinity, and zeta converges in distribution to zeta infinity. And there's some basic potential theory that says that once you have this convergence in distribution, the log potentials will converge to the log potentials of the limit, but only in a somewhat weak sense, in what's called the local L1 sense. So it's not quite pointwise or uniform, but it's this local in L1. And the Stokes transforms also converge. So as a consequence, knowing what the asymptotic random variables are, knowing what the asymptotic zero is, asymptotic critical points are, they tell you the asymptotic behavior of many useful quantities. So if you take the normalized magnitude of f, that will converge as n goes to infinity to the log potential of the asymptotic zero. The magnitude of f prime, if you normalize it properly, will converge to the log potential of the critical point. And the normalized log derivative converges to the Stokes transform. So if you know what these two limiting random variables are, that tells you a lot of asymptotic information about. So it's not that f itself converges pointwise to anything interesting. Right? We saw earlier that if you try to take a pointwise limit of f itself, you don't get anything interesting. But if you take a pointwise limit of these normalized quantities involving f and its first two derivatives, those converge to interesting things. Okay. So I had an example. I don't know how useful this will be, but so for example, if you take this polynomial z minus 1, if you try to take limits of this polynomial directly, pointwise limits, you get this very boring thing. As I said, this limit is either -1 or it's undefined or infinite. But if you take these normalized expressions, you get more interesting limits. So maybe I won't go through all of them, but I'll just go through one of them. If you take f of z, you take absolute values, you take reciprocal, log 1 over n, that converges to something more interesting. So for instance, if z is in the unit disk, f of z will converge to 1, and this will converge to 0. So this expression converges to 0 on the in the interior of the disk. But outside the disk, it converges to something else. So f of z goes to infinity, but it goes to infinity at an exponential rate. So as if z is outside the unit disk, this f of z grows like z to the n. And log 1 of f of z is then like n times log 1 over z, absolute value of z. And so this normalized limit doesn't go to infinity. It converges to something finite. It converges to log 1 over mod z. So you get an interesting finite limit, not outside the unit disk. So it doesn't go to infinity anymore. And all the other objects also converge to interesting functions, which are finite almost everywhere. Okay, and so it's because we normalize things properly. Okay, so there are many relationships between these. I'll just mention one other Yeah. So if you, another way of saying it is that the asymptotic limits give you asymptotics for so you can take all these previous expressions and like in the first identity you can solve for f of z, second one you can solve for f prime of z and so forth. And basically what this these asymptotics are telling you is that they're giving you asymptotic expressions. They're telling you what the magnitude of f of z should look like, what the magnitude of f prime should look like, what the log derivative looks like, and so forth. They give you asymptotic formulas for all these quantities. And you can integrate these and you can get some further quantities. So another nice identity, which turns out to be useful later. As I said, the Stoichkos transform, the Cauchy-Stoichkos transform controls these log derivatives. You can integrate this, use the method of integrating factors, and you can also relate the ratio. If you want to evaluate f at any 2 points, z0 and z1, there's a further useful relationship that the ratio between f, the value at 2 different points, is given by the exponential of the integral of the Stoichkos transform for some contour. You can pick any contour you like from one vertex to another, z0 to z1, and that you can just get by integrating this identity. The point is that if you understand the random variables zeta and lambda and zeta, you get a lot of information about your original polynomial. Okay, so hopefully I've convinced you that these limiting, it will be useful to know what these limiting random variables are. And so the first step in the argument is to actually give quite a good description of these random variables. So initially, all we know is that the random 0 is somewhere in the unit disk, and the random critical point is somewhere in this loon. But if if you need the origin, if a is converging to 0, so the limiting a is 0, then there's actually the situation is much more constrained. In fact, the random 0 and the random critical point, first of all, they have to converge to the same distribution. So asymptotically, they are the same. They have the same distribution, and they both live on the left semicircle, the left half of the unit disk. So that's what happens if you need the origin. And if you need the unit circle, what must happen is that the random 0 is uniformly, it spreads out and is uniformly distributed on the unit circle, and the random critical point converges to 0. It is almost surely 0. So actually, we prove more precise things than this, but this is the basic gist of what is proven. Okay. So why can we do this? Like, why is the asymptotic limit better than the non-asymptotic objects? And it's the reason is that in the limit, certain things go to 0. So, for example, I already told you that there are these relationships that the logarithmic potential of the zeros is related to the magnitude of f, and the logarithmic potential of the critical points is related to the magnitude of f prime, and the Cauchy-Stoichkos transform of the zeros is related to the ratio between f prime and f. But these are these three equations, but there are these two unknowns, f of z and f prime of z, and so there must be some relationship between these three quantities. So if you take the log of the third quantity and you compare it to the second, and you do a little bit of algebra, you find that there is a connection between the critical points and the zeros. The log potential of the critical points is equal to some constant times the log of potential of the zeros plus another constant times the log of the Stoichkos transform. Right? This just follows from playing around with this with these identities. Okay, so that's a formula. So for any fixed n, you could try to use this formula, but it's a little bit messy. But what you observe is that if you send n to infinity in the limit, this third term should go to 0 because the Stoichkos transform, lambda is converging to a limit. The Stoichkos transform is converging at least logarithmically in L1 to a limit. But then there's one of n is going to 0, and this n minus 1 over n factor is going to 1. So what you would expect when you pass to a limit is that in the limit you get a much simpler formula, that the logarithmic potential of the asymptotic 0 is equal to the local potential of the asymptotic critical point. Now, unfortunately, you can't quite justify this. There's a problem because sometimes the Stochastic transform gets very close to zero, and if it gets so close to zero, the log does not go to zero fast enough. Like if the Stochastic transform is exponentially close to zero, this factor can actually converge to something non-zero. So it turns out that this prediction is not always true. But what you can prove is that if you're outside the disk, if you're outside the unit disk, then you're away from the zeros and the poles, and the Stochastic transform you can show stays away from zero, and then this actually makes sense. Okay, so outside the unit disk at least. So these two local potentials, they don't agree everywhere, but they do agree away from the origin. So outside the unit disk, this is true. Okay, so for example, in this example that I gave before, where the zero is distributed on the unit circle and the critical point is distributed only at the origin, you can compute the log potentials. The log potential of lambda is log of max 1 of z. So it vanishes in the disk and it grows logarithmically outside the disk. But whereas the log potential of the critical points is log 1 over z everywhere. So it grows logarithmically outside the disk, and inside the disk it converges logarithmically to zero. So inside the disk, these potentials disagree, but outside the disk they agree. So in some sense, if you look at the zeros and the critical points from far away, they look the same. But if you look too close, they can be different. Okay, so what does this mean? Okay, so then you can start opening up your books on potential theory. Okay, and say, okay, so suppose you have two random variables and their potentials agree, at least outside the unit disk. What does this mean? Well, it implies many things. You can do a Taylor expansion in infinity, and what you find, for example, is that all their moments agree. So we already knew that the mean of lambda and the mean of zeta had to agree, but now also the variance have to agree. Well, at least, sorry, not the variance, but the expectation of the square must agree. Expectation of the third power must agree. Now, if we had real random variables, then having all the moments agree means that these two variables have the same distribution. Unfortunately, for complex variables, having moments agree doesn't necessarily imply that the distribution is the same. But still, this is a very strong statement. It also tells you, by the way, that the Cauchy-Stochastic transforms agree outside the disk. You can basically just differentiate the log potential to get the Stochastic transform. But there's a very nice interpretation from probability. There's this notion of which has this very appealing balayage, which I think actually means to like wash your hair or something, or to sweep out. But let's see, I'll draw a little picture here. So if you have a disk, radius r, okay, and you have a random variable which is supported in this disk. So there's a random variable which you call eta, which is living in this disk. You can form what's called the balayage of lambda. So you're sweeping out lambda to the boundary of this disk. It's called the way you define this is that you start with your random point eta inside this disk, and then you take a random Brownian motion starting at that point eta, and eventually this Brownian motion will hit the boundary of this disk, and where this point and there'll be some random point on this boundary, and that random point is called the balayage. Actually, technically, it's the density, the probability density of this distribution is the balayage. So it's basically if you randomly walk from your random point, you will eventually hit the boundary, and that boundary is the distribution of that boundary is called the balayage. In terms of potential theory, the balayage is the unique density on the boundary of the circle, which has the same log potential, so that the log potential of the balayage and the log potential of your original random variable, they agree, but they only agree outside the disk. They can disagree inside the disk. Okay, so for instance, if your random variable is only centered at the origin, then the Brownian motion will hit the boundary uniformly, and the balayage of the point at the origin would be just the uniform distribution on the boundary. If eta was at some other point, then the Brownian motion would be more likely to hit one side of the boundary than the other, and so the balayage will be what's called a Poisson kernel. It's large here, but small here. It will be a non-uniform distribution on the inner circle. Okay, so it turns out, this is a typo here. It turns out that the fact that the zeros and critical points have the same potential, an equivalent form of that statement is that they have the same balayage. That if you take any disk of radius r, so I'll draw one more picture here. That you take any disk of radius r bigger than 1, and you look at a random zero, which I call lambda, and a random critical point, which I call zeta. If you take Brownian motions from both zeta and lambda, then once they exit the disk, they look the same. That they have the same distribution as once you leave the disk. Okay, so for example, we had an example where the critical points were all at the origin, and the zeros were all on the circle radius 1. So these are very different distributions. But if you take random walks, if you take a random walk from the origin and a random walk from a uniform point in the inner circle, they both hit the this slightly bigger circle in the same way. That the distribution of the hitting location, they're both uniformly distributed on the inner circle. So so roughly speaking, if you take Brownian motions, if you diffuse both these random variables, then outside this disk they look exactly the same. Okay, so that's a very useful fact. Okay, so I can get rid of all this now. For instance, if you know that the zeros, if you know that the special zero A is converging to 0, that's one of the two special cases, you can now give a lot of information about the zeros and the critical points. So maybe I will just skip straight to the picture. Okay, so so if your zero is very close to the origin, then the critical points are all spread out. They must live inside this very, very thin loon between these two circles. Okay, and in the limit a goes to 0, and so the critical points are forced to lie actually on this semicircle. So the critical points, which are drawn in blue here, so we'll have some probably distribution on the semicircle. Okay, and this is the circle radius 1. Now, in this dotted line here, I've drawn a circle of radius 1 plus epsilon. Okay, and so we know that these balayages agree. So the zeros, the critical points, which are in blue, if you take the balayage, so you randomly move them by Brownian motion until they hit this circle. The balayage of the critical points and the balayage of the zeros must be the same for once you reach this slightly larger circle of radius 1 plus epsilon. And what this means is that the zeros, the random zeros, cannot have any mass outside of the semicircle. So here I've drawn a picture where the zeros have a little bit of mass. You know, maybe they have some mass over here as well, but they have a little bit of mass outside the semicircle. But you see, if the zeros had some, if the limiting zeros had some mass outside the inner circle, then with positive probability, the random walk Brownian motion starting from this portion of your distribution would hit this side of this dotted circle. But the critical points, which are in blue, almost all of the random walks coming from this distribution will hit the left semicircle, and almost none of them will reach the far side of the semicircle. So you can get a contradiction if the zeros have any mass outside of the semicircle, and so the zeros must also live on this semicircle. And once they both live on the semicircle, and since they all have the same moments, you can use Fourier analysis to show that in fact they must be the same. They have the same distribution. Okay, so that's how we control things when A is near the origin. Hang on, there's a, need to clear this. All right, to do the opposite case when A is near 1, this is trickier. So I had to use some rather ingenious arguments of Degoe, who also worked on this problem previously. So I won't describe all of it, but one of the key ideas is to exploit this perpendicular bisector theorem. That, so as I mentioned before, that if you have two zeros, lambda 1 and lambda 2, then the critical points cannot all lie on one side of a perpendicular bisector between two zeros. So that's a general statement. And in our particular case, this gives us what we call a zero-free region. It gives us a nice little region where we know there are no zeros. So again, I'll just draw a picture. Okay. So in this picture, A is close to 1. So our special zero is close to 1. And all the critical points are lying in this lune, this region between two zeros. And then if at these 2 points, if you draw unit circles between these 2 points, you get these two circular arcs. And so there's this little crescent-shaped region here between these two circles. And this is a zero-free region. So it turns out you can't actually have any other zeros in this region. So here I drew a red zero at this point here. And you can't actually have a zero here. This is not allowed. Because if you had a zero here, and you already had a zero at A, then you can draw the perpendicular bisector. And a little bit of elementary geometry shows you that if your point here is inside this crescent region, then the perpendicular bisector lies to the right of this lune. And so you see that all the critical points are on one side of this bisector. And this is precisely the situation which is prohibited by this Zago's perpendicular bisector theorem. So this can't happen. There are no zeros anywhere in this region here. The zeros can only lie outside of this region. Okay, so there is a zero-free region. Now you can work a little bit harder. So let's see, I'll clear this. Okay. So you can actually show that not only is your function 0 on this region, but there's actually a lower bound. It actually has size comparable to 1. It's bounded above and below in magnitude. Let me not say why. You have to use a quantitative version of the open mapping theorem, but I think I will skip this slide. And you can use this information to control these asymptotic zeros and asymptotic critical points elsewhere. So I think maybe I'll just go to the picture rather than give the argument. So, all right, so there's a region here where F is, yeah, so there was a region, where is my pen? Okay, so there's a region here where F of Z is basically is bounded away from 0, and in fact it's basically of size 1, as you can show inside here. And we also know that this normalized log derivative converges to the log potential of this asymptotic 0. So this log potential you can show actually vanishes on this region here. Now you can also show okay, so there's some additional arguments of Degoe that show that first of all the zeros have to asymptotically all live on the unit circle. That asymptotically, and this actually just comes from looking at f of 0. You use the fact f of 0 is the product of all the zeros. And you can control the size of f at the origin, and you can show that the zeros, which are this red distribution, all live on the unit circle, which implies that the log potential is harmonic. Okay, so that tells you that the log potential is harmonic in the unit disk. Okay, and now we can use, and here's where we start really using the asymptotic, the power of working asymptotically. We have the unique continuation property for harmonic functions. If a harmonic function is 0 on some open set, then it actually must vanish everywhere inside this disk. So actually, this log potential actually vanishes everywhere in this unit disk. And then you can take limiting values, and you can conclude that actually the zero distribution is actually uniform on the unit circle, which actually then lets you compute the log potential outside. So outside the unit circle, you can then show that the log potential is actually given by this log function, log 1 over z. You can also use a reflection principle to actually jump directly from here to here. But once you're outside the unit circle, the log potential of the zeros is equal to the log potential of the critical points. So now we also control the critical points potential. The critical points potential is also log 1 over z outside the unit circle. Now you can show that the critical points actually all lie on this arc here, and this comes from, you can use the fact that f prime at A is just n times the product of A minus the zeros, the critical points. Okay, so if you use this formula, and there's some elementary estimates of to go, you evaluate what f prime is doing at the center A, and you find that all these magnitudes have to be close to 1. Okay, that you can show that the zeros have to all lie on this line here, critical points, which means that this potential is harmonic everywhere outside of this little arc here. So once you know that that this log potential is log 1 over z outside the unit circle, you can also again use unique continuation and show that this log potential is also log 1 over z even inside the unit circle, everywhere away from this arc. And this potential only has a singularity of 0. And so if you use potential theory, you can actually therefore conclude that the critical points are all at the origin, at least asymptotically. So by using unique continuation, you can show that the zeros are on the unit circle asymptotically, and the critical points are at the origin. Okay. All right. So we have all this information about the asymptotic random zeros and critical points. Now, how do we get back to the actual polynomials themselves? So in the case when A is close to the origin, what we use is the argument principle and Richet's theorem. So these classical tools of complex analysis. And so again, maybe I think I will just refer to the picture rather than the text. Okay, so all right, so here is our situation. We have when A is close to 0, the asymptotically the zeros and critical points are living on the unit circle. So non-asymptotically, so for large finite n, the zeros and poles are mostly on near the circle. Sorry, the critical points are all inside this very thin loon. The zeros are also mostly near here, but there could be a few zeros outside. So there could be some density 0 set of zeros outside this loon. In particular, we have a special 0 here. Now we have this Stieltjes transform. So remember, where is my pen? Okay, so the Stieltjes transform, if you remember, is a normalized version of the log derivative. Okay, and the argument principle tells you that if you take any curve like this circle here, gamma, that the winding number of this log derivative, or equivalent to the winding number of this Stieltjes transform around 0, is equal to the number of zeros of f minus the number of poles. Okay, this is the argument principle, one of the basic things we teach our complex analysis undergraduates. Okay, so here in this case, sorry, the other way around. It's the number of poles minus the number of zeros. That's important. Okay, every zero has got a every zero of f creates a pole of the Stieltjes transform. Okay, so all right, so in this case, the Stieltjes transform has got at least one 0. There's a 0 A. So if you take a small circle around the origin, that circle will contain a 0 of A. of f, which is this a, and it will contain no poles because not poles of critical points. I'm sorry. Okay, every critical point of f gives you a 0 of this function here. All right. So there are no critical points inside the circle because the critical points are all in this loon. But there's at least 1 0. So this winding number is negative. It's -1. Okay. But on the other hand, if you instead take the winding number of the limiting random variable, see here, this random variable is so the limiting distribution zeros is only on the semicircle. So outside the semicircle is holomorphic. So it has no pole. It only has zeros. So it is at non-negative because there are only zeros here and no poles. So the winding numbers are different. But on the other hand, we know that the Stoichkov transform actually converges to the Stoichkov transform of lambda converges to the Stoichkov transform of lambda tilde. Now, if this convergence was uniform, we would get a contradiction because Rouché's theorem tells us that if two holomorphic functions are sufficiently close to each other, then the winding numbers they have are the same. And we get a contradiction. Now, it's a little more complicated than this because our convergence is only locally in L1. It is not actually uniform. But there's a trick. You get to pick this curve. So what you do is that you don't just pick any old circle. You pick a circle that stays away from the zeros and poles of S lambda. And if you pick the right circle, you can use the Peano principle. You can make this argument work. You can get your contradiction. But this is why I need this extra assumption. Okay, so there was this extra hypothesis that A was actually within a log, was within 1 over log n of the origin, and I needed that in order to justify this technicality here. Okay, so this is how you resolve, you finish off the conjecture when A is near the origin. When A is near the unit circle, the argument is more difficult. So maybe I'll just illustrate a special example. So we already talked about what happens when f is zeta -1. So there's a generalization of this example, which is very instructive. So you pick at A, which is close to 1, and you pick any polynomial, P of z, with some zeros in this loon. And you multiply it by a big power, not of z, but of a slightly shifted version of z. So you take, instead of z to the n, you take a shifted z raised to n minus a constant times a fixed polynomial. And then you subtract off not 1, but you subtract off whatever this polynomial is at A, and that will give you to force having a 0 at A. So there's a special class of polynomials which is very illustrative, and I worked with these polynomials first. Maybe again I'll just go to the picture. This particular polynomial, if you compute where its critical points and zeros are, this particular polynomial will have most of its zeros are very close to the unit disk. In particular, there'll be this special 0A, which is close to the unit disk. The critical points, there'll be a huge critical, so there'll be one point where the critical points are occur of high multiplicity. And then there'll be a small number of zeros and a small number of critical points in this loon. So there will be this particular polynomial, the critical points and zeros look like this. And if you can fit all the zeros inside the disk and all these other zeros outside, critical points outside this loon, you would get a contradiction to Sendov's conjecture. So if you want to prove Sendov's conjecture asymptotically in the case when A goes to 1, you have to rule out this particular type of counterexample. So you can do this by you can analyze the zeros of this particular polynomial by Taylor expansion. So this is the polynomial. You can work out what the zeros are. Okay, if you have a 0, then you only have a 0 when these two terms agree, and so you can take logs, and you get some you get some relationships. You could be connecting the zero of your polynomial f and the zeros of the polynomial p. So I use lambda j, lambda 1 to lambda m, to denote the zeros of this polynomial. So you can manipulate this formula. You do a little bit of Taylor expansion, and what you find is that the zeros do lie close to the unit circle. So these zeros, they are almost on the unit circle. They're on the unit circle with a shift, and then this is other shift. And you take this formula, you plug in this ansatz, and you want lambda to stay less than 1 to stay inside the unit circle. And after a little bit of Taylor expansion, what you find is that if you want to make the counterexample work, you need a certain inequality to hold. Okay, so there are these parameters C1 and C2. Okay, so I didn't. C1 is the location of. Let's see. Oops. C1 is the location of A. A is like, it turns out. Oops. Sorry. A turns out to be 1 minus C1 over n in this. Okay, and C2 is the location of this critical point. Okay, and if you want the critical point to stay outside of this disk, you want C2 to be bigger than C1. So there are these two constants here, and then there are these extra zeros here. So in this example, you have a few zeros that are lying outside, not close to the unit circle, but they're just somewhere in this loon. And if you want all the zeros to lie inside this disk, what you find has to happen. After enough Taylor expansion, you find that this particular equation, this inequality, has to hold for all theta. Okay, so as you go around the inner circle and you want to check that all the zeros stay inside the disk, you need a certain inequality to hold. But it's very hard for this inequality to hold because, as it turns out, this expression, as I said, this is always non-negative. These expressions turn out to also be non-negative, and that's because these zeros lie, all these zeros lie in this loon, and it turns out that in this loon, this expression is always, at least, is always non-negative. But because of the cosine, this expression has mean 0. Okay. Actually, this is because you're on the average. Actually, I should say. Okay. And so, so the left-hand expression has non-negative mean, and the right-hand side has 0 mean. And so the only way that this can actually that you can actually have this inequality is if first of all there's an equality here. This vanishes, and all these lambdas, these guys have to make to 1. So in fact, all the lambdas actually have to lie exactly on the circle. Yeah, this is the only way in which you could make this inequality work. But you can still rule out this inequality if you take, if you look at Fourier coefficients. Yeah, if you take the second Fourier coefficient of this identity, okay, so you integrate it against either 2 pi theta. And you just do a little bit of work. If you inspect the second Fourier coefficient, what you find is that you must have vanishing second moment. This is a phenomenon that actually was observed in previous literature, that the zeros, often their second moment, their variance, their second moment happens to be extremely small. But this turns out to be impossible. And so there's the final geometric effect that ends up being used is that you can prove that the zeros all lie on this arc. Okay, but if you lie on this arc, the zeros cannot, the square sum cannot actually sum to 0 because the square of all these numbers, when you square these numbers, they will lie on the left half plane, and they when you square them, and they can't sum to 0 unless they're all 0. So in fact, the only case which is at all problematic is the case where all the zeros of lambda lie at 0, which is basically this one example. Where all the critical points lie at 0. This is basically the only case in which you could possibly come close to violating Sandow's conjecture. But that case, of course, even that case, still Sandow's conjecture barely holds. So this is the most delicate case of the analysis, and there's a few more slides, but I think I will stop here because I'm out of time. So thank you very much for the opportunity to give a presentation here. I think I will stop.
Okay, dear Professor Tao, dear guests, on behalf of the International Center for Mathematical Sciences in Sofia, I would like to thank Professor Tao for agreeing to give this talk in our center on his recent results on the Sandow's conjecture. So it was a great honor for all of us to have you as a speaker. And now I would like to open the Q&A session. If you have some questions or some comments, please feel free to ask. You can use the raise hand button or just directly ask your questions. I see here Professor Ognian Kunchev is raising a hand. Professor Kunchev, you have the floor.
Okay, thank you, Willy. I first want to thank Professor Tao, Terence Tao, for the very nice talk and the very nice introduction, by the way, to the topic, and also for presenting a very nice mixture of ideas. And I understood, the main ideas, and what I wanted to make is actually a remark. The remark is about the point of using potential theory and the balayage techniques there. I have to say that there was a very nice group here in Sofia, and maybe you have heard about Dimitar Zidarov's works on balayage and partial balayage. This is the name of Dimitar Zidarov. He's very much now pretty famous among the people working in potential theory and the balayage. And Zidarov and Sandov were friends. That's what I want to say. Yes.
Okay.
Zidarov was 10 years old, actually. Zidarov was born in 1922 and Sandov in 1932. So but they never talked about these problems.
They should have.
Who brought them together, maybe now in the skies. So that would be also interesting to other people, physicists. Zidarov was a physicist. He was not. Yes, he was a physicist. So he actually was solving the inverse problem. He was trying to identify a body, a heavy body beneath the Earth. And he was using potential theory. So that's why he invented the partial balayage. And this was very important. Actually, he solved theoretically and practically the problem was solved also here in Sofia by his pupils at the Geophysics Institute. He didn't work at the Institute of Physics, but the Institute of Geophysics. Okay, so this might be an interesting to you and also to other people. So thank you for bringing together Zidarov and Sandov. Thank you.
That's a great connection. I was not aware of that.
Yeah. Okay. Thank you once again. That was my remark.
Any other questions or comments?
I think there's one in chat.
There is one question in chat from
Have I
Mr.
tried to? Yes, have we tried to work out Smale's conjecture with this technique? Yes, actually, yes. So Smale's conjecture is another unsolved question about the relationship between the critical points of a polynomial and its values. I did take a look at that. Unfortunately, this technique. So I need very much this compactness to get started. And so what's very nice in the Sandov conjecture setting is that all the zeros and all the critical points are all contained inside a compact set, the unit disk. And I have looked at Smale's conjecture, which is, I don't remember the exact form here. It's like a variant of the mean value theorem. But what happens is that even after you try to normalize things as best you can, the zeros and critical points, they all go off to infinity. And I've not been able to extract out a very useful limit. So this technique, maybe if one is clever enough, one can do it. But I did try. I was unfortunately not able to apply it for that other conjecture.
There is a question from Christo Sendov, who is a co-author of Bogovet Sendov and his nephew. Do you see the question?
Yes, right. Yes, I know Bossier did propose some additional conjectures where you don't assume that the zeros are all in the disk, but you just assume that somehow on average they're in the disk. You take a p-th mean. I looked at that too, and again, there's the same problem. I don't have enough compactness. So now the zeros can all, enough of them can drift off to infinity that I lose control. Somehow Sendov picked just the right conjecture that you can do something. You change it a little bit, and then you can't actually make progress with these methods anymore. Yes, I did have a look at that. Again, maybe there's a clever trick or something. Yeah, so it could well be that something can be done. For instance, actually, so there's this earlier result I mentioned of Bojanov and Ratti and some other person, that if you enlarge the disk of radius 1 to 1 plus a little bit, 1 plus epsilon, then the Sendov's conjecture is true for large enough n. So they have the particular radius 2 to 1 over n. So the analog of that is that weaker result is not known yet for Bossier's version of the conjecture. So that would be the place to start, I think, is to first understand that what can be done there.
May I add some words about academician Sendov? I met him many times, both in Sofia and Moscow. And last time I met him 2 years ago in Moscow, when he was giving a talk at the meeting of Moscow Mathematical Society about his conjecture. That's the whole talk was about this conjecture. And he was very enthusiastic about proving this conjecture. And he said that he believes that it will be proved in next years. Unfortunately not, but we still hope that it will happen in next years. So thank you for your talk. It was exciting. Yeah.
Okay, thank you.
Any other questions? If there are no questions, let's thank Professor Tao again for this brilliant lecture. And maybe Oleg would like to say some few words at the end.
Yes, I would like first to thank Terry for this very, very nice lecture. And because he mentioned that he never visited Bulgaria, please remember that you always have an open invitation to come to Bulgaria. We will be very happy here because some people know you, and as far as I see, many mathematicians, you will have interesting discussions here in Bulgaria with the Bulgarian mathematicians, Bulgarian specialists. So thank you very much.
Yeah, it's a pleasure.
Finally, I would like to thank all participants for this wonderful evening, afternoon, and morning. Thank you very much.
Okay.
Okay. Okay. Thank you.
Okay.
Thank you. Thank you. Thank all the friends.
Yes. I would like to thank also the president of the Bulgarian Union of Mathematicians, Professor Nikolov, for his help to organize this evening, and also to Lyudmila. Thank you very much, guys. Thank you.
Thank you. Bye-bye.
Okay.
Bye.
Bye.
Thank you. Goodbye.
Bye. Bye.
Thank you. Bye-bye to everybody.
Bye-bye.
Indeed, bye-bye to everybody.
Till the next non-virtual meeting in Bulgaria.
Yeah, the first meeting. At least I attended.
Okay.
Веско, ти попита за Митрофан.
Yeah.
Ами, за съжаление, в болница сменили са болницата и в момента все още се бори. Даже му помагат с кислород, да видим. Ще стискаме палци всичко да бъде наред.
Дано.
I would like to thank also to Toshko, who did Todor Brazov, who did an excellent work. Thank you very much, Toshko.
There are still some comments in the chat.
Да. Да. Yes. Okay.
Fascinated by the life that's getting
Yeah. Jenny, just read this if you want. Yeah. Jenny will read some of the.
A preferably anonymous student to everyone. I'm definitely not educated enough on the entirety of this topic, as the talk exceeded my level of understanding around 30-40 minutes. I also haven't made myself extremely familiar with Sanders' conjecture, but I'm really fascinated by the life work that's happening in mathematics, and accordingly, I'd like to know why this conjecture was so interesting, important in the first place. From my experience with conjectures, the really popular and worldwide known ones tend to have some practical theoretical importance. So how would you describe the case with this one conjecture? What sparked your interest and kept you motivated to solve it? And how would you explain your motivation to a person fairly unfamiliar with that particular conjecture, in case it's even explainable without all of the prerequisites? Thanks a lot. I'm really honored to be able to attend a live talk with such a community.
I'm afraid Terence Tao is not in the list of participants now, because he mentioned he has other duties, but I can transfer all these questions which appeared now in the chat to him by email, and maybe he will answer in his blog on his homepage.
I may add, in his blog, Terry Tao answers a similar question. So go there, and not only his answer, but also different people from our community have given their arguments about the popularity of this conjecture.
Okay. Good night to everybody. You are leaving.
Yeah, good night to Alec.
Good night.
Bye.